How tiny errors grow until nothing works. It starts with something so small it feels irrelevant. A rounding error, a delay, a tiny mismatch, and somehow everything collapses. To understand how tiny errors grow into total failure, we need to rethink what error actually means. In stable systems, mistakes fade. They are corrected, absorbed, or canceled out. Noise stays noise. Precision is forgiving. Small deviations are expected, tolerated, and quietly dissolved back into equilibrium. Error exists, but it does not accumulate. It leaves no lasting trace. The system possesses what engineers call negative feedback, a natural corrective tendency that pulls behavior back toward a stable center. When something drifts too far in one direction, forces emerge that guide it back. This self-correction happens automatically, embedded in the system's structure rather than imposed through constant monitoring. The errors that do occur become learning opportunities rather than threats, informing adjustments without creating cascading consequences. But many modern systems are not built this way. They are tightly connected, highly optimized, and fast. Speed is rewarded. Precision is enforced. Redundancy is stripped away in the name of efficiency. Margins are narrowed. Buffers are removed. In these systems, small errors are not dampened. They are carried forward, stored, reused, amplified. What once would have disappeared now persists, embedded into the system's ongoing behavior. Every calculation feeds into the next without pause for verification or recalibration. The architecture favors throughput over resilience, creating long chains of dependency, where each link relies on the accuracy of everything that came before it. There is no room for graceful degradation, no pathway for errors to dissipate harmlessly. Instead, they become part of the operational memory, influencing decisions and calculations that ripple outward through time. This matters because tiny errors are unavoidable. Measurements are imperfect. Timing drifts. Information arrives late. Sensors disagree. Models simplify reality. Interfaces lose nuance. These flaws are not failures. They are the cost of interacting with the real world. No instrument captures truth with infinite precision. No clock synchronizes perfectly across distributed components. No communication channel delivers messages without some degree of latency or distortion. What determines survival is not whether errors exist, but how the system responds to them over time. Does it treat imperfection as an anomaly to be eliminated at all costs, or as an inevitable condition to be managed with wisdom and flexibility? At first, nothing seems wrong. Corrections compensate. Adjustments smooth out discrepancies. Control mechanisms do exactly what they were designed to do. The system appears resilient. In fact, it may even perform better as it fine-tunes itself. Outputs tighten. Variance shrinks. Precision increases. Confidence grows. The system appears to be learning, improving, becoming more exact with every cycle. Dashboards display encouraging trends. Metrics move in favorable directions. Stakeholders observe what looks like continuous improvement, a steady march toward operational excellence. The feedback received suggests that the system is not just functioning, it is thriving, adapting, and optimizing its performance in real time. But beneath this apparent success, something subtle changes. Each correction now depends on the accuracy of the last. Buffers shrink further. Tolerances tighten again. Slack disappears entirely. The system becomes more sensitive to the very errors it once ignored. What used to be noise becomes meaningful input. What used to be harmless drift now demands response. Sensitivity increases faster than understanding. The system begins operating closer to its theoretical limits, with a margin between acceptable and unacceptable performance narrows to a razor's edge. This heightened sensitivity creates an illusion of control. Every small deviation is noticed and addressed immediately, but this responsiveness comes at a cost. The system loses its ability to distinguish between meaningful signals and irrelevant fluctuations. Everything becomes urgent. Every deviation triggers intervention. Eventually, the smallest deviation no longer fades. It accumulates, and once accumulation begins, error stops being noise and starts becoming structure. As errors accumulate, the system begins drifting away from its original assumptions. Models still apply, but to a reality that no longer exists. Corrections are calculated against outdated states. Each adjustment is locally correct and globally misaligned. The system believes it is correcting itself, but it is correcting toward a moving target it can no longer see clearly. The mathematical relationships that once described its behavior with reasonable accuracy now represent an idealized version of what the system used to be. Parameters drift, boundary conditions shift. The environment evolves in ways the original design never anticipated. Yet the control algorithms continue operating as if nothing fundamental has changed, applying yesterday's solutions to today's problems. This is where amplification begins. Each small error feeds into the next decision. Timing slips propagate downstream. Rounding differences compound silently. Delays overlap. Dependencies magnify tiny misalignments into systemic distortion. No single error is catastrophic. Each one looks tolerable. Together, they reshape behavior in ways that are hard to reverse. What appears as a collection of independent, minor issues is actually a coordinated drift in system behavior. The errors are not random. They are correlated, reinforcing each other in subtle ways that create momentum in a particular direction. Reversing this momentum requires more than fixing individual problems. It requires understanding how the problems interact and feed each other. What makes this phase especially dangerous is invisibility. Performance metrics can remain stable. Outputs stay within acceptable ranges. Dashboards stay green. Reports look normal. The system appears healthy while internal alignment erodes. Observers see success. The math sees divergence. The traditional indicators that organizations rely on to assess system health continue showing positive results because they measure outputs, not internal state. They capture what the system produces, not how it produces it. The growing misalignment between internal reality and external appearance creates a false sense of security. Decision makers believe they have time to address issues gradually, unaware that the system is approaching a threshold beyond which recovery becomes exponentially harder. Feedback loops tighten under these conditions. Responses arrive later, but with greater force. Adjustments overshoot. New corrections are triggered by the corrections themselves. The system begins reacting to its own noise. Control turns inward. Stability mechanisms start amplifying instability instead of suppressing it. What was designed as negative feedback, corrective action that restores equilibrium, transforms into positive feedback that drives the system further from stability with each iteration. The control system becomes part of the problem rather than part of the solution, adding energy to disturbances rather than dissipating them. This creates a false sense of control. The more aggressively errors are corrected, the faster they propagate. Precision becomes a liability. Flexibility disappears. The system becomes brittle, dependent on perfect inputs that can never exist in the real world. Operators and engineers double down on what they believe works. Tighter tolerances, faster responses, more aggressive intervention. Each escalation seems justified by local evidence. Each adjustment produces short-term improvement that validates the approach. But the cumulative effect is a system that can only function under ideal conditions, conditions that reality rarely provides. At this stage, failure no longer requires a shock. It only requires time, because the system is now amplifying what it was designed to ignore. The conflict becomes undeniable when corrections stop stabilizing the system and start destabilizing it. Efforts meant to restore accuracy introduce greater distortion. The system chases precision and loses coherence. Fixes stack on top of fixes, each one locally justified and globally destructive. Engineers implement patches that address immediate symptoms while deepening underlying pathologies. Every intervention creates new dependencies, new edge cases, new opportunities for unexpected interactions. The complexity of managing the system grows faster than the ability to understand it. This is the emotional peak, the moment when engineers, analysts, or operators realize that doing the right thing locally is making the global outcome worse. Every fix adds stress somewhere else. Every adjustment creates a new imbalance. Expertise becomes a trap because experience reinforces responses that no longer apply. The very skills that made someone successful in managing stable systems now produce counterproductive results. Intuitions fail. Standard procedures backfire. The mental models built through years of practice no longer map to reality. This realization brings frustration, confusion, and sometimes despair. The recognition that competence alone cannot solve the problem because the problem has transcended the domain where competence operates. Mathematically, the system has crossed into positive feedback. Errors no longer cancel out. They reinforce each other. Small deviations are echoed, magnified, and returned with greater intensity. What once behaved linearly now behaves explosively. Cause and effect stretch apart. Prediction collapses. The elegant mathematics that describe stable operation give way to nonlinear dynamics, where small changes in initial conditions produce wildly different outcomes. The system enters a regime where forecasting becomes impossible, where the future state depends sensibly on details that cannot be measured with sufficient precision. At this stage, blame becomes tempting but meaningless. No single mistake caused a failure. Each step followed the rules. Each correction was justified. The collapse emerges from interaction, not incompetence. The system did exactly what it was designed to do, just not what it was designed to survive. Searching for a root cause becomes an exercise in frustration, because there is no single point of failure to identify and fix. The failure is systemic, arising from the collective behavior components that individually function correctly. This makes accountability difficult and learning even harder, because the traditional frameworks for understanding failure, human error, equipment malfunction, design flaw, do not adequately capture what happened. The most dangerous aspect is timing. By the time the pattern is visible, reversal is nearly impossible. Shutting the system down may cause immediate damage. Letting it run guarantees eventual collapse. Every option carries cost, and the window for graceful recovery has already closed. The system has accumulated so much internal distortion that there is no smooth path back to stable operation. Any intervention vigorous enough to restore alignment risks triggering the very failure it aims to prevent. The choice becomes not whether to accept damage, but what kind of damage to accept and when. The conflict is not between accuracy and error. It is between tolerance and perfection. And perfection has already pushed the system past its breaking point. The resolution comes when systems stop treating error as a defect and start treating it as information. Mathematics makes this clear. Error cannot be eliminated. It can only be managed. Systems that survive are built to absorb imperfection without amplifying it. They incorporate mechanisms that recognize error as a natural feature of operation rather than an aberration to be suppressed. This shift in perspective changes everything, from how systems are designed, how they're operated, to how performance is evaluated. This changes design philosophy completely. Buffers are reintroduced. Tolerances are widened. Corrections are slowed instead of accelerated. Instead of chasing exactness, systems prioritize stability across a range of conditions. They accept imprecision early to prevent catastrophe later. Designers build in slack, extra capacity, redundant pathways, delayed responses that allows the system to absorb shocks without immediate reaction. This slack may appear inefficient under normal conditions, but provides the flexibility needed when conditions deviate from normal. The goals shift from optimization to robustness, from peak performance to reliable performance across varied circumstances. Small errors are allowed to exist because suppressing them creates larger ones in the future. Variability becomes a diagnostic tool. Noise reveals stress before failure appears. Flexibility replaces precision as the measure of robustness. Instead of treating every deviation as a problem requiring immediate correction, operators learn to distinguish between noise that carries information about system health and noise that simply reflects the inherent variability of real-world operation. This discrimination requires wisdom, patience, and a willingness to tolerate imperfection in service of long-term stability. The deeper lesson is counterintuitive. The most reliable systems are not the most accurate. They are the most forgiving. They expect drift, delay, and mismatch, and they remain functional anyway. Their architecture assumes imperfection and builds resilience around that assumption. They degrade gracefully rather than failing catastrophically. They maintain core functionality even as peripheral systems malfunction. They prioritize survival over optimization. When error is acknowledged early, collapse is avoided. When it is denied, it grows quietly until nothing works. Understanding this difference is not just technical. It is a line between systems that adapt and systems that break the moment reality stops being perfect. How